Everybody, today we're going to go ahead and look at the last video lesson for the gases chapter, and this one's on kinetic molecular theory and real gases. So far what we've looked at gases and kind of basically just talked about what was happening. We never really talked about why any of these things were happening. We just talked about what would happen if we did something. If we increase the temperature, what would happen to volume? If we increase the pressure, what would happen to the volume? If we increase the temperature, what happens to the pressure, so on and so forth. So we're just looking at what happened. We also would look at if we had a chemical reaction. If we had a chemical reaction, how much product would we get and how much volume or pressure or whatever, the problem happened to be. But none of those explain the why. And that's why we need a theory. Theories always tell us why things happen, and that's the premise behind the idea inside. So that's why those are laws. They're gas laws because they don't tell us what happens. I'm sorry, they tell us what happens, but they don't tell us why. So here we're going to try to answer the why. In order to do that, we need to first look at what's called the kinetic molecular theory. Now in the notes I use KMT for kinetic molecular theory. Feel free to do that on your homework, do it on your tests and quizzes. I know what we're talking about when we mention KMT. So this is done over a number of years by a number of scientists, and what they did was they figured out some general information regarding gases. Now this idea of the kinetic molecular theory is going to be used with solids and liquids as well as gases. So we kind of talk about them from a perspective of a gas, but we can actually use these things with some tweaking and modification when we talk about liquids and solids in a later chapter. Alright, so the postulates are essentially the points or the stipulations of the theory. So the first one is that we have gases are composed of tiny particles. Alright, so all that means is that when we have our gas in our container, we're going to say that the gas is made up of little tiny pieces. Okay, well, it makes sense. There could be molecules, could be atoms, depending on what we're talking about, but that's the first assumption, is that they're little tiny spheres. The second assumption is that they have no volume. Alright, now that's where things get a little we hit a little bit of a problem here with postulate number 2, because this particle has to take up a volume, right? I mean, it has to take up space if it's going to be a particle. I mean, that's what all particles do. Alright, so this is the postulates for what's known as an ideal gas, and that's the key here, is that these postulates are for ideal gases, and the idea is that an ideal gas doesn't have a volume. Yeah, I know, it doesn't make any sense because there is no such thing as an ideal gas. Kind of bear with me here. We're creating a falsehood that we're going to try to get to. We're going to try to get to that point as we look at the next couple slides. Alright, so the average kinetic energy is proportional to the Kelvin temperature. That's okay. What that is saying is that if you increase the temperature, if temperature goes up, the kinetic energy of the particles go up. Now you should know something about kinetic energy. Kinetic energy is the energy of motion. So what that is saying is simply is that these particles, if I increase the temperature, are going to move faster than if I had the temperature lower. If I have a lower temperature, they move slower. Higher temperature, they move faster. Okay, and it makes sense, right? Kinetic energy goes up, temperature goes up. The other one is that the gas particles have no attraction force. So if we were to look at those gas particles and say, oh, wait, if we, expand the container and make those particles a little bit bigger, what we're saying here is that those particles are not going to attract each other. Now this postulate is important, and we need this postulate because if these gas particles don't attract each other, it will never turn into a liquid and it will never turn into a solid. It will be perpetually a gas forever. So postulate number 2 and postulate number 4 have some issues. Alright, and there's a reason for that, and we're trying to make the work very simplistic. And what we do in science is we try to create this really simple model, and then we look at the real world and say, okay, how can we make the real world become close to these ideal situations? Okay? Alright. So we want to make the attraction force be 0. We don't want this attraction force to exist. And we want to make the volume of the particles 0 as well. Alright, so let's take a look. So for ideal gases, it's going to be a gas that completely obeys all of the postulates of the kinetic molecular theory. All right. Now there is no gas that really does that. There's no gas that we've ever discovered that completely obeys all of those postulates. They're always going to vary from that because all gases can condense down into a liquid phase, and eventually most of can turn into a solid. So real gases, what we can do is we can make them approach ideal behavior. They're never going to be perfect, and that's why when we look at our calculations, and especially in that last lab we did, data doesn't always work out because we're assuming that we have an ideal gas when we really have real gases in the world. All right, so let's continue. All right, so real gases are going to fail to some degree. We're going to have some sort of failing in our real gases. So when do our gases become the most ideal? Here are the conditions that we want to have in order for real gases to be the most ideal. And that would be at low pressures, i.e. a large volume, and at high temperatures. Okay? Let me show you some data to back this up. So this is really important. That you want to remember this. The postulates are important that were on the second slide or the first slide with data, and this information about how real gases become ideal. All right, so let's take a look at some quick data here. This is a graph. What it's showing is pressure, volume over RT. Now if we put everything in here, if I put 22.4 liters, 1 atmosphere, 22.4 liters for the volume, temperature at 273 Kelvin, and my pressure, my moles should be equal to 1. That's what I should get. I should get moles equal to 1 if I'm using STP conditions. Remember, standard temperature and pressure. Alright, so if the gas is ideal, this should stay 1 no matter what I do. That would be the ideal. But notice what happens as pressure goes up. As the pressure goes up, my gas starts to become less and less like an ideal gas. The other gases start to become less and less like an ideal gas. So as pressure goes up, the gases become less and less ideal. So the key here is to have low pressures, and at low pressures, when my pressure is very low, close to 0, then my gas is the most ideal. So gases are most ideal when pressures are very low. Same thing with temperature. Take a look over here. Here again, we're keeping pressure, is increasing here because we're changing temperature. But again, PV over RT, the number of moles should be equal to 1. Well, as temperature goes up, we're going from 200 to 500 to 1,000 Kelvin. Notice what's happening to this. Now, this is all the same gas. Over here, I had different gases. This is all the same gas, and I believe this was for nitrogen gas. So as temperature goes up, notice what happens to this line. It starts off being really crazy, and then it gets more and more straighter, and then straighter, and it starts to flatten out. So as temperature goes up, what we're going to see is our gas becomes most ideal. So why is that? Why are gases becoming more and more ideal at low pressures and high temperatures? Well, it has to do with the two things we're trying to ignore. If I have a little tiny container, my volume is really small, what happens to pressure? Well, if volume is low, my pressure has to be pretty high. So we go ahead and put my gas particles in here. And notice that they take up a lot of that space. Right? So if I were to try to figure out what the volume of this container is, wouldn't the volume of the container be the volume? Hold on one second. My daughter was knocking at the door. I had to answer her question real quick. Okay, so what I was trying to say was the volume of the gas, okay, is going to be equal to the volume of our container. So I'm going to use a C for, I'll just say contain. So that's the container. So that's the size of the box, right? So the size that the gas is in. But keep in mind that the gas particles themselves are taking up space, right? So the gas particles, we have to subtract out the volume of the particles. Now, if this is really small and this is relatively large, then this is going to change quite a bit. But if I make my pressure really low, what has to happen to volume? Volume has to go up. So if I have a large volume, bigger container, and I take the same amount of gas that I have in here, and I just move that gas from here, and I move it into here, notice that now this number goes up dramatically, and the amount of space that this is taking up is really, really small and negligible. And I can pretty much say, you know what, even though this is true that these particles are here, this will drop out. And I can say that the volume of the gas is equal to the volume of the container, which is what we've been doing. Right? And if I make the volume even bigger, I'm not going to drop, but if I make the volume get even bigger, then I can say that this drops out even more and more. But that's always going to be here, and this is always going to cause our gases to deviate a little bit. Now, the other one is that if we have our gases in a container, I'm going to make the particles really big and just focus on two of them, there is an attraction force between them. Remember, we talked about this attraction force. This could be hydrogen bonding, it could be London dispersion forces, it could be dipole-dipole. Now, obviously, the stronger the attraction force between the particles, the more likely they're going to stick together. And if that happens, then when this particle attempts to bounce into the wall here and create pressure, or hits the wall and creates pressure over here, the attraction force is going to slow it down. So our pressures aren't going to be the right value. Okay, so we're going to have to correct for their pressures. Our pressures aren't going to be what we're expecting them to be. So how do I compensate for this? How do I make this attraction force go away? Well, what I do is I increase the temperature. Think about it. These two particles, if I have this particle here, let's draw again. Okay, I got it sitting right here, and I have this particle right here. Well, as I bring this one close, as I bring this particle closer, whoops, isn't the attraction force going to start to adhere, and all of a sudden it's going to, boom, it's going to stick together, and they're going to start to liquefy. All right, but if I cause the particle to move faster, it's going to start being attracted to it, but it's not going to be as attracted as it should be, right? Because it's going to have a faster motion. So if I, remember, increasing temperature increases kinetic energy. So these particles are going to move past each other really fast, so they can never cause that attraction force to happen. But if I lower the temperature, this particle comes near, it's going to be attracted to each other. So higher temperatures, higher kinetic energy, they zip right past each other, and no connection between the attraction forces. So we can say at high temperatures the attraction force is ignored. Okay, so those are the two things we want to minimize, the volume and attraction force. And I also get some students to ask me questions. Well, I'll say, well, what do we do with real gases then? What do we do when we don't have these conditions? Well, Van der Waals figured a way to do this. And what he did was he corrected for the pressure and he corrected for the volume. Notice that you've got P, V, and RT. So what he's doing here is he's taking the pressure that we would observe and he's correcting for. Remember I said that the attraction force would cause a deviation in that pressure? So that's what he's doing here. Okay, over here we have a correction for the volume, because remember I said the particles in here are going to contribute to that volume. So that's what he's calculating right here, is figuring out this, and he's including the attraction forces. So we're never going to use this equation, because obviously, look at me, this is crazy. These letters here are experimental constants that have to be looked up based on the conditions and the type of gas you have. Most of the time they're actually calculated in the lab itself. So we're not going to actually plug into this equation. I just wanted to give you an idea of there is a way to handle real gases. What we want to do is we want to minimize this, to chop out this portion so we don't have to worry about it. Chop out this portion so we don't have to worry about it. And how do we do that? We want our pressure to be very low and our volume to be very high. Let's try that again. And our volume to be high. We would like our temperature also to be very high. So those are the conditions to make this true, so that we can just focus on PV equals nRT and make our work a lot easier. Alright guys, I'll see you in class. Bye.